those one through examples. So you know what is a hyperplane arrangement is? It's just the collection of finite hyperplanes. So here, let me just again tell something about our field. So we are fixing our field is either R or complex numbers. And V is a vector space of dimension L. And these are HIs are just hyperplanes. In V, which means they are affine subspaces of dimension of codimension 1. So these are affine subspaces of codimension 1, which means that each hyperplane is just a zero of linear polynomials in L variables, right? So HI is nothing just the kernel of some linear equation or linear polynomial. So if I'm saying kernel, so it means that linear polynomial. And because here we are considering the affine one, so this means that there will be some shift as well. Because otherwise, if you are considering just a subspace of codimension 1, it will be generated by just a linear polynomial, which is a homogeneous one. But here you are considering the affine one, so this means that you have some D here, right? So okay, so just here and in this is okay. So for example, if you are considering L2, which means that you are in plane, either the complex plane or the real plane. So here our hyperplanes are just lines, right? So our hyperplanes are just line, which means that, for example, here, okay, one more thing, let me just recall that one. This is the defining polynomial, which is just the product of all linear polynomials describing H, I mean hyperplane. So for example, in this case, we can consider x by x plus 5. So this means that x is equal to 0. Is this one, right? X is equal to, oh sorry, y is equal to 0 is this line, and x plus y is this one, right? So this is my arrangement for this one, for this defining polynomial, right? And this is central one because the intersection of all hyperplanes in this one is just 0. Which is not, right? We can have another example here, which is sort of this defining polynomial is xy and x plus y is 1. Oh, sorry, or maybe I'm not. Okay. Yeah, that's fine. And here you can see that the intersection is empty, so it's affine one. So this is affine, and this is central. Right? You can see that there is another possibility if you are considering this L equal to 2. In this case, we can have 3 parallel hyperplanes, which means 3 parallel lines as well. This is another example, right? So here is the polynomial is just, you can see that x minus 1, x minus 2. Right? Okay, that's great. Okay, here we are not considering anything like what is K, or K is either a field of real numbers or a complex number. But if we are just considering this setting in a real number, then we can see that if we will remove these lines from our plane, then we have disconnected space, right? So this is a disconnected space which has 1, 2, 3, 4, 5, 6 components. And each component is like homotopy equivalent to the point or homotopy equivalent to the plane. Right? So here again, you can see that this is again disconnected one and you have some component. This is again in this case. But if you will just consider the case when you are considering the complex plane, then this is not disconnected, right? This is not disconnected at all. And this is just one component in C2. It's in C2, which means a complex plane, right? And so here, what is interesting object to study in hyperplane arrangement is this topological space, which is called the complement of arrangement. And this is V minus the union of all hyperplanes, right? Okay, so is there any question regarding the conic or deconic construction? So I should recall that one, or it was fine. Yeah.
Actually, I have a very good conclusion. Usually, hyperplanes are one-dimensional less than the ambiguous space. Then we consider the three-dimensional space, then we are having a two-dimensional.
Which means the planes. Yeah.
So can we see a hyperplane in three-dimensional, like if we consider the four dimensions?
We can't see the hyperplanes of. I mean, in R4 we can't see the hyperplanes of dimension 3. I mean, the spaces of dimension 3. But for example, if you are in R3, then when you can see that the hyperplanes are just planes, so in that part we can see. But I mean, when you are in higher dimension, you can't see those things. But one thing which we can do by the coning and deconing construction, you can see that if you have something like in L3, I mean, when you are in higher dimension, you can by deconing, you can down into the lower dimension. But this is only true for the central arrangement, right? But this you can do, but only for the central arrangement. For for not affine one. So that's why conic and deconic construction gives you either you can discuss affine arrangement or central one. Whatever you want to choose to work with, then either you can work with central one or you can work with the affine one. Okay, there was another notion which. Okay.
So
yeah.
So again, maybe yesterday that person was somebody asked. I just want to be sure about the topology of existing. This is a topological space. So of course, I mean, in terms of Zariski topology, it is also it is open set. So it also induces Zariski topology on it. This M of A. So are we?
So here you are taking the ambient space is Rn. So you are just considering this one. I mean Kn. So you are just considering the topology as in Kn.
The usual one or the
yeah, it's the usual one. It's a usual one. So in conic and deconing construction, if you remember, we have seen this one. If you will decon this thing, then you have this relation. So this is the reason you just need to just see that you can work with either the central one or the affine one, because you have such a nice relation. So if you have started with the central one, then definitely you will have this one. So for example, let's just do some calculation by using these formulas or relations. So for example, if you have a central arrangement with n lines in K2, K2 means here I'm just considering C2, because you know that that's a trivial case when we are considering the real case. So we have these n lines are here. So what do you think? What will be the topology in that case? It's a topological question, maybe. I don't know. You have seen something like that or not? but let me just, so let's just apply this result here. So if we will decon this one, decon means that we will have one dimension less here. So we will be here in C, right? So which means that this is my line, complex line, and you are missing because we are removing one line because we are fixing one coordinate which is just like x naught, who is the zero set of the coordinate x naught. So this is, you can assume that this is your x naught is equal to 1, and you are removing that one. So this means on this line you are just removing these n-1 points. So for example, you are just taking the line when x naught is equal to 1. So you are removing this line as well because we are not taking this one in our setting. So that's why, because it's some sort of parallel to this one, because this is x naught is equal to 0. So I think so this is not right line. This one. So this is x naught is equal to 0. This is x naught is equal to 1. So on this line, you can see that there are only n points. So this means that you are just this m, the decon of this one is just c minus n-1 points. Right? And you know that
what was deconing geometrically?
Decon means that you are just fixing one line here, which like here I have fixed x naught is equal to 0, and you just take the parallel, have a line here which is x naught is equal to 1, and you just take that one. So this my line is this one. So
And this line is just a translated one of,
yes.
Okay, the
X1
nth one. Okay.
So you have this one, and you know if you have some background in topology, then you can see that this is nothing but the wedge sum of circles, n-1 circles, because each, for example, if you have just a complex plane, complex line, which means that you are plane, and you are just removing one point from that one, this is nothing just homotopically equivalent to the your circle. So C star is nothing, just homotopy equivalent to circle. And if you are removing n-1 points, so definitely you will get n-1 copies of circles which are joined in this way. So this is called the wedge or bouquet of the circles, n-1 circles, right? Because each point give you a loop, which is non-trivial one. So this means that if you want to see what is the topology of this one, is nothing just is the n-1 bouquet of circles times, because this is again homotopy equivalent to S1, so that's why this is the this is, so the complement of this arrangement is actually homotopy equivalent to this one. The wedge circles of n-1 circles, and then you will take the product with S1. Okay, so if you have any questions.
Any question from IBA side on these explanation, particularly regarding to the topology of coning and deconing?
No, is there any question?
So you mean, okay, deconing is related with C star. So it means just lift by S1, lift by S1.
Because this is just a simple example in complex plane. So definitely.
So this figure is going to be the donuts, joining of the donuts.
It's like not donuts. Actually, this is this one. This is the bouquet of circles.
But with cross with S1.
Yeah, it's cross S1. It's like you will donuts or the toruses.
Torus is joining.
Like bouquet of toruses.
Bouquet of torus. Ah, okay.
Sort of.
bouquet of flowers or bouquet of circle?
पहले सर्कल था वो
पहले
जब क्रॉस
circle.
S1 किया तो फिर वो बुके ऑफ टॉरस बन गया
Actually, this is-
Shaheen, it is better to explain
Circle.
Okay, I will
Of
explain
circle.
later maybe.
Of-
Maybe when you will see some homology part, cohomology, then you can realize what's going on there. Maybe.
S1 cross S1 is a torus. Okay, then when you wedge with this, so each S1, each piece of the circle will cross with S1. So that will be the torus. So all the circle will become the torus.
Okay, now is there any question? So I can just about the reducibility or irreducibility of hyperplanes. So for example, I had given one exercise to you. So you have to check the braid arrangement is reducible or not. So let me just recall what was the definition of the product of two hyperplanes. So you are given two hyperplane arrangements in some V1. This is given in V2. So this is nothing, just the direct sum with V2 whenever H1 is in A1 union V1 direct sum with H2 where H2 is in A, right? So if you can find your, if you can see that your hyperplane arrangement can be written as a product of two arrangements, then you call this one is reducible, otherwise it is called irreducible. So last time we have seen example of Boolean arrangement, which is actually reducible, and Bohar that's reducible in that way. So the Boolean arrangement let's call it A and B. So that has actually L component, right? And each AI is corresponding to the hyperplane, the coordinate hyperplane, right? So for example, the A1 will be the corresponding to X1, and this one will corresponding to XI, right? And what are our VIs here? VIs are just K, I mean of dimension 1. So VI is just, and here we can write here the coordinate of each VI. So these are just points here, right? Okay, so my question was about, so I asked for the braid arrangement. So let's rewrite this braid arrangement in this way. So the polynomial of the braid arrangement was the product of these hyperplanes. Right? Okay, if you look, why it is called braid arrangement, if you will look the complement of this arrangement, so you can see that these are all elements in your V such that xi is not equal to xj for all I. So this is nothing, just the configuration spaces of ordered n points. And its fundamental group is actually called the braid group. So that's why it's called the braid arrangement. Right? So this is the reason to call it. Braid
Shaheen,
arrangement.
let's take the opportunity to just say what is the configuration space for the participant.
Okay, so
Yes.
actually, okay. So this is actually the definition of the configuration space of n points or n ordered points. So, so what are you doing in that one? Actually, you are just you are taking some vector space, and there you are just considering the n distinct points, right? So you are just assuming. So the definition is actually the same one which is written here. So this is actually called the configuration space of n points, ordered n points, because here the ordered method, I mean which coordinate you have used. There is another configuration space with unordered points, but this is the ordered points. Okay, so my question is again, is it reducible or not? What can you see? So if you will look this arrangement is actually has non-empty intersection. So you can see that if you will just, and what is that one? Can you see? Or can you tell me what is that one?
All coordinates equal.
All coordinates.
All coordinates. So this
The
is a
diagonal.
point such that x1 is equal to x2. Okay. So would you try to see it is reducible or not? So my grade arrangement is actually lies in the, which is KL. But you can observe that if I will just take this vector space, which is defined in this way, the sum of all coordinates is 0. This is a vector space, subspace of V, right? Okay, that's great. So this is like a hyperplane for me, because it is defined by a single relation, a single linear polynomial. So, any guesses?
Yeah.
What?
L components of x1, a hyperplane of x1 intersect cross with a hyperplane of x2. Sorry, x1 is equal, xi is equal.
This arrangement, what we can do this with this arrangement, we will just take this arrangement and we can just translate, just take the trace of this arrangement on this subspace. So that is my V1, A1, which is actually the line here. I know my V double bar, which I'm saying here, x such that x, where this one here. Because I need to take V as a V prime, or let me just call 1 and 2, so that's why it will be easier. So here you can easily see that if this is your V1 and this is your V2, then V is nothing, this is the sum of these two subspaces. Right? If you remember from the linear algebra course, what is the direct sum is you have this subspaces, and you can see that the intersection just contains 0, right? And what else you have here? Its dimension is L minus 1, and its dimension is 1. So it means that this is just a sort of a vector. I mean, you can write every vector split in this part, right? Okay, and A1 is just the trace of this arrangement of the given arrangement to this one. Because here what you can do, you can just fix one variable and you can replace that variable into the other variable, as you have said. This has some redundant part. Okay, so what is in V2 here for us? Can you guess? So this is nothing, just the trace of VR on V1. And what is this one? Such that we have VR is nothing, just A1.
What do you mean by trace for VR?
I mean, you have just taking one, so you have, because this relation gives you, you can pull out one of the coordinates from there. So
Okay.
that's why you have just defined in this your arrangement. Right?
What is VR? Okay.
What is VR?
Braid
is
complication.
our braid
Okay,
arrangement.
okay.
Because if you will look here, every hyperplane is covered through this one. So there is nothing left here. So it's
This is zero.
actually the empty one, empty ring. Right? So you have this relation because when you will write each hyperplane in this setting, so you will get your required hyperplane, required arrangement.
So still this is irreducible? With
Which
the
one is
anti-arrangement?
reducible? So this is, yes, this is, so this shows that dr is
Irreducible.
reducible.
Empty, do we
Empty
count
is allowed there.
allowed there?
Yes. If it is non-empty, then it is called decomposable.
Empty means two
Let's have
parallel
some-
lines or maybe n parallel lines. They are not
No,
intersecting.
empty means there is nothing. No
No
hyperplane,
lines.
no hyperplane.
So it will exist every time. Then all the arrangements will be reduced.
Not every. We will see. Not every. So I will give you another example in which you can see that that is irreducible.
But it's a condition of V1 and V2. V1 and V2.
V1 and V2 are just subspaces in V such that
Okay.
they have the direct sum is exactly equal to V, right? Okay, one more interesting thing, you can see that this arrangement which you have here, A1, that is actually irreducible. So you cannot further reduce this arrangement, A1.
We will not view this arrangement directly by looking at the relation of V2. So for instance, if someone look X1 is equal to X2.
It's mostly depending on this part and this part. Because here you have intersection non-empty and it's one-dimensional space. So that's why this one-dimensional space is giving you nothing, which is sort of related to this part. And the rest of the part is just coming from this space. So that's why you don't need actually here something. Okay, an example where this is not, but this is irreducible.
The thing is coming from algebra. So this is a completely geometrical setup.
Sorry?
One can't view through the relation through the algebraically. So this is completely geometrically. Everything is deterministic.
It's also algebraically as well.
But again, V2 is coming through the intersection, and intersection is.
Okay, we will see more about it when we will discuss the essential one. So then we will see that how we are doing this. Okay, there is an example which is usually called the tree arrangement. So there is its defining polynomial is x, y, z, x plus y, x minus v, y, sorry, x plus v, x minus v, y plus v, and y minus v. So you can see that what are these hyperplanes in R in K3, right? So this polynomial, sorry, this arrangement is irreducible. And here you can see that the intersection of all and you can actually if you will want to see what is this one, you can just decode this one and you can see that in KL what is this arrangement is. This arrangement is nothing just like this one. So can anyone say something about why this one is irreducible, or why we don't have such a splitting here in this way?
When you are checking reducibility or irreducibility, so you checked after homogenizing or after
No, it's
deconing?
not necessary.
So anything
Your
which
space is
which
either
is set
central one
for
or non-central one. We can just start
from here to.
I mean, if I will decon this one, then this is that intersection will be just empty one. But still, if it is irreducible, then decon is also irreducible. So reducibility means that you have to find such a coordinate which you can split from the rest of the part. But here is no such coordinate because x, y, z are all there and all involved in these settings. I mean, you can't free one of the variable from there.
So this is the algebraic
Yeah.
terminology.
So that's why this is irreducible. Okay, so I have another definition which was essential. So is there any question? Please feel free to ask questions.
Can you explain the same point in the above example?
Okay, because in the above example, you can see that all these because we can set all these hyperplanes on this setting. Some of these two are 0. Some of all these coordinates are 0. And this gives you one relation here. But here is no, you can't find such. I mean, the main idea is coming from this intersection. Here is you have just a one-dimensional space.
And
here we don't have such.
Here it is homogenized sort of structure. That is not homogenized.
That is homogenized as well.
That Z is not there in the product in the beginning.
What is not there?
When you homogenize it, every time you put
But that is
the only component Z.
But that is, yes, but it is already central one. I don't need to homogenize it.
Okay.
Or you want to see in the projective space, or that's something else.
You understand my point when I say Z should appear all along in the product according to your definition?
Sorry?
Of only the component Z should appear when.
No, there is no Z. They are just with these L variables at this moment. Okay, so the essential arrangement was, you will say that your arrangement is essential if it satisfies this condition that its intersection is of dimension 0. Right? So here you can see that so of course, if your arrangement is a fine one, so intersection is empty, so this is not the case. So every essential is central one, right? And the first condition you can see that first relation. So this means, for example, here you want to see that this is essential or not. Yes, this is essential because its dimension is 0. But here you can see that this is not essential, right? So this the graded arrangement is not essential. And but if you look the Boolean arrangement, that is again essential. Right? If you remember, when I have defined the lattice, so this is this is an element of the lattice, and this is the maximal element of the lattice, right? And that gives you the rank of the arrangement as well. Right? So this gives you the rank of the arrangement, which is actually equal to, in this case, is, what is that one?
Minus 0. 2 minus 0.
No. If you know that the intersection is of dimension 0, right? And this is the maximal element. So what will be the rank of my arrangement? So rank is the co-dimension.
So this is going to N1.
L. Because this is 0. So co-dimension is L. So this L is actually the same as the dimension of A. From where we have started, from the our vector space. And here you can see that if you will consider the rank of A is L minus 1, but its dimension is L. Right? Its dimension is L. And that's why when you will see the notation for the braid arrangement, usually you will see this notation for the arrangement, but it is lying in L,
Yeah.
because this is describing the rank of that arrangement. And here you have, because this is essential one, and here you can see that the rank of this arrangement is same as L as the dimension of A.
And ambient space in all cases is KL, right?
Sorry?
Ambient space is KL.
Here, yes. So from here you can see that when your arrangement is not essential, you can always reduce that one in such a form. And this setting is true for every central non-essential arrangement. And even you can generalize this one for the affine arrangement as well, which is non-essential. Is there any question? Okay, is there any question? So please ask, because I'm now moving to the combinatorial part.
Geometrically, how do you define the dimension of an arrangement?
Oh,
I
it's
forgot.
just the dimension where it's not. This is the dimension of your arrangement. It's depending on your ambient space. And the rank is depending on the arrangements. I mean, the hyperplanes which you have chosen in your arrangement. Okay, now let me do one calculation for the lattice, intersection lattice of the arrangement. So I will pick one example and we will make the Hasse diagram of that lattice, and then we will conclude the Mobius function for that one, and then we can calculate the Poincare polynomial for that arrangement, right? Okay, so let's consider this example. This one. Okay, so you know that, okay, so this is the picturing actually in our K2. Right? I mean, it's a picture of the concept of this arrangement. So you can see that this is just like a K2 and these are just lines in K2. Right? So if you remember, the intersection lattice contains all intersection points which are coming through these these hyperplanes. So here you can see that if I will start, so you know that this V is always a part of your intersection lattice. So let me just start a little bit.
What is the difference between essential arrangement and central arrangement?
Central and essential. This is central one, but it is not essential, Because for essential, you need have this condition. The dimension and the rank must be same. If this is not essential, still by using this setting, you can come down to this arrangement, and here you will just get an empty arrangement such that this will become essential one, because its rank is now L minus 1 and it is lying in L minus 1. If your arrangement is not essential, then definitely you can.
Is there any relation between the rank of BR and the rank of A1 and A2?
Here the rank is yes. Here is the rank is no. As such, there is no relation. But here rank is L minus 1.
That is the same as the rank for.
Rank of B.
But in general, there is no relation between.
Not at all. Maybe I don't know, but generally I don't think so. For example,
And what?
here we have this thing. Here you can see the rank is L, and here rank, everyone has rank 1.
Yeah, so it's a kind of decomposition coming there. What do you define the rank of the empty set is -1 or 0?
So V set is there in your intersection lattice. This is always there. So which means that V2 is, if I'm talking about A2, and A2 is empty one. So this means that V2 is always there. So this is just rank 0. Whenever you have a single element in your arrangement, definitely your rank will be more than 0. Which means one hyperplane gives you at least one rank.
Apparently, it is the sum of
Yeah.
the ranks. Yeah.
Yes. It's splitting means that your rank will be sum of. It's like the dimension as well.
Yeah.
So here dimension is L minus 1. Here dimension is L. So that's fine. Okay, so we are considering this example now, and we are making the Hesse diagram of our lattice, our intersection coset, which is just have all elements are just the intersection of these hyperplanes. So first of all, I need to fix all these hyperplanes there, and my minimum element, which is of course rank 0, the whole ambient space. And then we have these, how many hyperplanes are there? Okay, let me just write instead of, so we can, because we want to see the intersection as well, so I need to just write precisely what are these. So maybe x is equal to 0, y is equal to 0, and z is equal to 0. X is equal to y, x is equal to minus y. I'm going to read that. So x is equal to 0, y is equal to 0. These are 9 hyperplanes. Right? So maybe okay, then we have intersections, right? So for example, you want to see what are the intersection, you can just pick the points from here. Right? So for example, okay, So let me just draw the deconic one, because in this way you can easily see that what are the intersection points, right? So it would be good idea to work with the deconic part. So this means that I will just remove this z from here, which means that I'm just substituting z as a 1. 1, 1, 1, and that's it, right? So here you can easily see that in my diagram. So this is x is equal to 0, this is x is equal to 1, this is x is equal to minus 1, this is y is equal to 0, y is equal to 1, y is equal to minus 1, and this line is x is equal to y, and this is x is equal to minus 1. Okay, right? So in this way, you can easily see that what will be your intersection lattice. So this point is actually, you can see that what is this point? Can you guess? This is minus 1, right? And this is 0, minus 1. This is minus 1, minus 1. Sorry, this is minus 1, minus 1. Minus 1,
0. The second point.
Second point. Oh, sorry. So
0 minus
0 minus 1.
0 minus
right?
1.
0 minus 1, right? And this is 1. This is 1 and minus 1, right? Okay, here we have y 0, x is equal to 1. So it's very easy to see what are your points, right? This is 0, 0. And this is minus 1, 0. And this is minus 1, 1. This is 0 and minus 1. Oh, sorry, 1. And okay, the last one is 1 and 1, right? Okay, that's great. So let's just list out all these points here. Okay, so let me just 1 minus 1 and so on, right? Okay, maybe I'm not writing in good setting, but that's fine. Okay, so we have all these 9 points out here. Now we will just link these ones. So this point is here. So I will make this one as a edge. So let me just write these boxes. So point is here. So here, because I'm not assuming this part, so I'm just removing here. This is 1, this is 1, 1, 1. Okay. Okay, now you can just link, you can make the edges between any two numbers if this is a subspace here, right? So 0 minus 1 is here, here. So this is connected with this, all these 3 lines, and this is connected with this one and this one as well. X is equal to y means that this is connected with this one, and this one. Right? And if you will go x minus y, so this means that you have either 1 minus 1. Sorry. So I have y. Sorry, this is not correct. So this is here, and this is here. So x is equal to 1 means that when you have x is equal to 1 is here, x is equal to 1 is here, x is equal to 1 here. X is equal to -1 means that x is equal to -1, x is equal to -1, y is equal to 1 means that this is connected to here, here, and here. And y -1 is here, here, and another one. This. Right? Okay. Perfectly fine. So, is there another step here? Yes or no? No. Yeah, that's great. Because this is 0 rank, this is first, and this is the second, and that's the end. Right? Okay, now what we can do. So if you remember when I have defined this Mobius function, that you can just see that we want to actually calculate for any number which is this one. And what is this one? This Mobius function satisfies this relation if you are taking the distance from x to x. Maybe it's called, let's call it distance 1. It's always 1. But if you want to, you have this when they are not equal and x is less than y, then you will, what you will do, you will just okay. So it satisfies this relation as well. So for example, if you are given x and y, so what you will do, for example, this is my point here, and because you want to calculate all starting from b and ending at some point x. So for example, if your x is this one, and you have to start from here. And by definition, this mu of v is always 1 because mu of v is 1. So that's why mu of v is 1. So this is always 1. And what is this one? Because you have just one direct relation between the hyperplane and your space v. So this means that this is the only one relation, which means that this function, the value of the function from here plus the value of here must be equal to 0. So this gives me -1, right? And similarly for each case, for each hyperplane, you will get just -1. Okay. Now let's see this one. Yeah. Question? So let me just take some. Okay, now if we want to calculate what is the Mobius value here, so what we need to do, we have to go down when it is going down. So this gives me this, the Mobius values of all points here gives me 0. Right? Because here you are picking any element which is lying between x and y. So you have to pick any points here, which means there is all hyperplanes which are lying between this point and this p. So all are these here. Only these 3 are here. These terms will not calculate anything to calculating Mobius function for this point. Okay, so we have already calculated these things here. And what will be the answer here?
2. All sum to 0.
Oh,
Because here is -1,
Plus two,
-1, which means -3, plus 1, which is -2. So it must be 2.
Plus 2.
Can you guess here? No?
It is not symmetric.
1. That's the right answer. Because this point is actually the multiplicity with 2. Right? That point has the multiplicity 3. Which means that 3 planes are involved there. Right? But here are just 2 planes are involved. Okay, let me just draw this with some different one. Oh. So if you will have this one, this means that you can go this, and you have this. So 1 minus 1 plus something makes 0, which means that this must be 0. And similarly, you can put the value of the rest of the intersection point. So this will be 2. So here is 1, 2, 1. This is 3, 2, 1. This. Right? Okay, that's great. Yes. Any question?
The one in blue should be 1, right?
Yes, this is 1. Because blue shows you this picture. Because these are the only two hyperplanes which are lying between V and this point. So you will just calculate the sum of all Mobius values must be equal to 0 due to this relation. So we know that because we will just do this one step by step. Because at 0 rank we know, at 1 rank we know, and for 2 and further for 3, 4, you can just use this formula and you will get your answers.
Okay, thank you.
Right? Okay, any questions so far? No? Just last thing which we will just calculate what is the Poincare polynomial in this case.
This is always monic one.
Yes. Oh, sorry. Yeah, it's the rank of 6. Okay, so you need to start from the 0 rank, right? Because there is only one point here and its rank is 1. So this means that coefficient is 1 with T0.
What is this term called?
What is?
This term called?
Which term?
Poincare polynomial.
Is Poincare polynomial. Because whenever you have intersection lattice, I mean any poset, geometric poset, you can always make this polynomial. Okay, now let's calculate the coefficient of 1, which means all terms or all points which have the rank 1. You will just consider those 1. So every time you can see that here is -1, and how many minus 1s are there? 8. So this will gives me 8. Actually -8, but because here is minus t power 1, so that's why you will get just 8. What is the coefficient of t square?
9, I think. 1, 2, 3,
40.
7.
40.
14.
14. Yeah. Because 2s are 1, 2, 3, 4, 5, and then which makes 10, 11, 12, 13, 14, right?
Okay.
So this is your Poincare polynomial. Okay, so okay, maybe in this discussion session we can do a lot of about the Orlik Solomon algebra. Happy?
Now, any question from the audience?
Yes. Is there any question?
From IBA side? So we have made a lot of taweez today anyway. So have you calculated the IBA Karachi ko dikhayenge ab?
Okay, one small thing. This Poincare polynomial, if you will substitute t is equal to 1, this gives you something. Can you guess what is that one? Especially in the real case. What?
number of regions,
Yeah, it's
When we
number of
take a-
connected components.
components, yeah.
So this gives you actually number of connected components. It's called zero. So actually this is Betty 0.
Hmm.
In this case. Because this has just trivial homology. Other than that,
All higher level homologies are
zero.
zero. Yeah.
So this is the only non-trivial Betty. So is there any question? No question.
Question.
That's all. No
Okay.
question. Okay.
Thank you very much, IB Karachi. Now you can leave too, and we are now heading toward all the participants toward the tea, and maybe we continue with the discussion further on these particular points. Thank you, Shaheen. Thank you very much.